Thank you very much. So thank you, Barbara and Neil, for the invitation. For me, it's really a pleasure to be here and to discuss in this Candela lecture about the properties of quantum fluid of light. So before to start entering the detail of the subject, so I would like to try to give an idea of what a quantum fluid of light is. We are probably all familiar with the standard, let's say, quantum fluid, so matter quantum fluid, like, for example, liquid helium and ultra cold atoms. So, and we know that these quantum fluids can exhibit very striking quantum coherent effect, collective effect, like superfluidity or Bose-Einstein condensation. But of course, the situation for the light is quite different. Indeed, the light beams, are composed by a large number of photons, no? But in the vacuum, photons do not interact. And typically, optics experiments are dominated by single particle behavior. So then, in order to observe a collective macroscopic behavior with light, we need to solve two problems. The first one is to give a photon a mass, because of course photons are massless, and also we have to be able to engineer an effective photon-photon interaction in order to try to observe collective behavior of light. So, and this is possible using, first of all, nonlinearities. So, for example, if you have a light beam which is propagating in a chi-free medium, so the nonlinearity in the medium allows to engineer an effective photon interaction, which is repulsive. This is the first point, so use nonlinearity. And the second point, to attribute an effective mass to a photons, what we can do is to use the spatial confinement of the photon. We will see that confining photons in a cavity, or just using the paraxial approximation, the fact that a laser beam has a Gaussian shape in the transverse profile, it is possible to attribute a mass, an effective mass to a photon. So with these two ingredients, in principle, we should be able to observe a collective behavior of light and then to have a so-called photonic quantum fluid. The first, so to the best of my knowledge, the first time in which this analogy, let's say, between the propagation of light in a nonlinear medium and the behavior of a fluid was pointed out in this paper here, which is quite old, in 1993, in which the authors pointed out the fact that the nonlinear diffraction phenomenon can allow to observe the generation of vortices and turbulence in light beam, in analogy, which is also happens in, let's say, in normal fluids. And some years ago, in 1999, there was this proposal by Raymond Chow and co-worker, in which it proposed to observe Bogoliubov dispersion and superfluidity in weakly interacting photons in a two-dimensional photon fluid. So indeed, in this proposal, the idea was to use a Fabry-Perot cavity with a nonlinear medium inside. And this is exactly what we have done, let's say, 10 years after, using a Polyton microcavity. So we will discuss in detail in the following. So then we can define, classify the fluid of light into families. main families. The first one is based on cavity configuration. So we have photons confined in a cavity that interact typically with the nonlinear medium. So this is a case of microcavity polaritons, and also, for example, in the case of Bose-Einstein condensation of photons in optical cavities filled with dye molecules. I think that one lecture of this series was indeed devoted to this topic and was given by Martin Weitz. And then we have a second family of quantum fluid of light based on cavity-less configuration. This is even simpler. So there is just a light beam that is propagating in a nonlinear medium without cavity. And in this, to this category belongs the so-called photon fluid in propagating geometry. The medium that provide nonlinearity can be different media. So in particular, rubidium vapors, photorefractive crystals, thermo-optics, liquid, and so on. So these are the two main categories. So in our lab, we have both these platforms. So one based on polariton fluids, so based on semiconductor microcavity in which we can create polaritons. And I will describe in details in the first part of the talk the behavior of these polariton fluids. And then the second platform is based on propagating geometry configuration, and we use as a nonlinear medium a hot atomic rubidium vapor. So there are some differences that we will that I will explain in the following between the two platforms. So basically, the polariton fluid are well suited to study out of equilibrium dynamics system, out of equilibrium system, while the propagating geometry can also model dynamics of conservative. This brings me to the outline of the talk. So I will start with the polariton platform, and I will show, after a short introduction on the system, I will show how it is possible to observe the collective and measure the collective excitation in a polariton fluid, in particular, how it's possible to measure the Bogoliubov dispersion, and also I will show that it is also possible to observe the so-called ghost branch in this system. So then I will show you that polariton fluids are a very interesting platform to study the driven-dissipative out of equilibrium phase transitions. In particular, in this framework, we have recently observed the appearance of a ghost on mode when we can generate, we can observe a spontaneous symmetry breaking in the system. And we have also demonstrate that inhibiting the spontaneous symmetry breaking of the phase of the system, we observe the destruction of this ghost on mode. Finally, for the polariton platform, I will show that they are, so this platform is very interesting also for quantum simulation of astrophysical objects. And I will show briefly our work, which is still in progress, in order to simulate black holes with this fluid oscillator. In the second part of the talk, I will show you that it is also possible to obtain a quantum fluid of light in hot rubidium vapors using the propagating geometry. And in this case, I will show how it is possible to measure the Bogoliubov dispersion. And I will show some examples of the versatility of this platform that allow to study turbulence and quantum turbulence and vortex interactions. Okay, let's start with the system, the polariton system. So the physical system which is under investigation is the so-called semiconductor microcavity that we can see here, that is constituted by a quantum well here, which is placed between two Bragg mirrors. Okay, so then this system is equivalent to a Fabry-Perot of very high finesse with a nonlinear medium inside. So by laser excitation, it is possible to create exciton inside the quantum well. And the space, so of course, the exciton are confined in the z direction due to the presence of the quantum well, but they are free, let's say, to move in the transverse plane of the structure. And the specificity here of this structure is that it is possible, so quite easy, to achieve the so-called strong coupling regime between exciton and photons. In this case, when we are in this strong coupling regime, two new particles appear that are the so-called microcavity polariton, that are linear combination of exciton and photon. So polariton are half light, half matter quasi-particles that are composed by an excitonic part and a photonic part. I have reported here in this graphic here the dispersion curve for the system. So we have here the energy as a function of the wave vector in the transverse plane. Indeed, as I have already pointed out, so the exciton and then the polariton are free to move in the transverse plane. So the polariton fluids are essentially two-dimensional fluids that live in the transverse plane of the structure. So this is the dispersion curve. So energy is a function of the wave vector in the transverse plane. And then we can see here in blue, this parabola is the dispersion curve of the uncoupled photon, so the photon in the cavity. And we see that due to the fact that the photons are confined in the cavity, they acquire an effective mass. Indeed, they have a dispersion which is parabolic, like a dispersion of a massive particle. And this is due to the confinement of the photon inside the cavity. The exciton here, of course, the exciton are also a massive particle, so then the dispersion has to be it is also parabolic, but in this case, we cannot see the curvature because the mass of the exciton is very large with respect to the effective mass of the photon. And then, due to the coupling, we can see in green the appearance of two new dispersion curves, the so-called upper polariton branch and lower polariton branch, that are well separated in energy here by the vacuum Rabi splitting. So, so the important point here to retain is that we have quasi-particle, half light, so half photons, and from this photonic part they acquire very light mass, and half exciton. So, and from the excitonic part they can interact non-linearly with each other. So they exhibit strong nonlinear interaction. So then, all in all, because the polariton also have a spin, they can be described as weakly interacting composite bosons. And indeed, they are very interesting systems to study quantum coherence effect in this polariton fluids. Probably one of the most celebrated example of quantum bosonic effect with polariton is the observation of the so-called polariton Bose-Einstein condensation. This experiment was done in 2006 in the group of Benoît Devaux and Lesidang, respectively in Lausanne and Grenoble. And here in this experiment, the systems, also the polariton microcavity, was pumped out of resonance, so with an energy very large, very high, with respect to the polariton energy. So then the excitons that are created in the structure relax very efficiently, and polariton accumulate in the ground state here of the lower polariton branch. When the threshold for condensation is crossed by the system, what is observed is the appearance of this macroscopic population in the ground state, accompanied by the narrowing of the emission in the momentum space around the k=0 wave vector, which is the smoking gun of the polariton Bose-Einstein condensation. So this is a non-resonant excitation, which is very interesting to study the appearance of this Bose-Einstein condensation. There is also another kind of excitation that allow us to create polaritons, is the so-called resonant excitation. So in this case, using a resonant laser, we can create a polariton fluid in a specific state, so controlling very precisely the different parameters of the fluid. In particular, we can control the density of polariton fluid, and this is done quite in a simple way, just controlling the intensity of the resonant excitation of the laser beam. We can control the speed of the polariton fluid because we can inject polariton here on different wave vector in the transverse plane of the structure. So, for example, here we have a certain wave vector. If I inject the polariton here, of course, the wave vector in the transverse plane is less than this one, and then the velocity, the speed in the transverse plane of the polariton fluid that I am creating is also less important. Okay, so, and then we can also control the phase of the fluid, because the phase of the fluid in this resonant excitation is innervated by the laser phase. So we can imprint the phase of the laser in our polariton. And this is an interesting configuration, this resonant excitation, in order to study the quantum hydrodynamics of a polariton fluid. And we used this configuration in the past in order to demonstrate superfluidity and Cherenkov wave, for example, or also the observation of dark soliton and quantized vortices in this system. So in the case of resonant excitation, the dynamics of a polariton fluid is described by this equation that I've written here, which is a so-called driven-dissipative Gross-Pitt-Hayeski equation. So which described basically an out-of-equilibrium system. Is a generalized form of the Gross-Pitt-Hayeski equation, which is used also to describe the Bose-Einstein atomic condensate. We can have a look at the different terms. So the first term describes the kinetic energy of the fluid. This term here describes the presence of an external potential. Could be useful to model the presence of an obstacle on the flow of the polariton fluid. This is the very important term which describes the nonlinear polariton interaction, which is proportional to the polariton density. And then we have two terms that are not present in the standard Gross-Pitt-Hayeski equation, which describes the equilibrium system. These terms here represents the pump, the laser that inject polyton in the system. But polyton are so the lifetime of the polyton is quite short, of the order of, let's say, 10, 20 picosecond in the standard cavities. And then they relax, emitting photons that at the end, eventually they escape from the cavity, no? And then we have also the loss, this term here. So these two terms are specific of the polyton quantum fluid that are driven-dissipative system. This equation here, and the steady-state solution of this equation exhibit bistability behavior. And this is not very surprising because, so as I said before, the system is equivalent to a Fabry-Perot cavity with a nonlinear medium inside. And it is well known that this kind of device should exhibit bistability. In particular, when the system is pumped with a pump which is slightly detuned in the blue with respect to the lower polyton branch here, we can observe a typical bistability curve, present here, no? So then, in order to fully characterize the behavior of a quantum fluid of polytons, what we have to know are so it's the behavior of the collective excitation of the fluid. So we have an homogeneous fluid, we generate a small perturbation on the top of this fluid, and we want to know how this perturbation behaves, how it propagates and so on. And in order to do this, so we have to use the so-called Bogoliubov treatment. So the important point here is that due to the fact that the system is a driven-dissipative system, the behavior of the collective excitation strongly depend on the working point on this bistability curve. So the collective excitation behaves differently if I'm working here, here, and here. So then we will see this different behavior. Okay, in order to describe the behavior of the collective excitations, we have to use the Bogoliubov theory. So the standard machinery. So first of all, we linearize the Gauss-Pitarievsky equation around its steady-state solution. So we can write the wave function of the polyton like this. So the steady-state plus a small perturbation. So then we can derive an equation of motion for the weak perturbation here. Described, so which is governed by the Bogoliubov operator, and diagonalizing the matrix of the Bogoliubov operator, we can deduce the dispersion relation for the collective excitation that is called Bogoliubov dispersion. In our system, this is the typical formula that describe the Bogoliubov dispersion of the collective excitation. And we can see here that we have a positive and a negative solution. Now, as I pointed out before, this, let's say, this dispersion relation and then the collective excitation, the behavior of this collective excitation depend on the point in which we are working on the bistability curve. Let's start with the first very remarkable point, which is called sonic point. This means that we are working here exactly at the turning point of the upper bistability branch. We drive our system here, and for this specific point, it is possible to demonstrate that the tuning that we put on the excitation, is the tuning delta here, which we can find here in Bogoliubov formula is exactly compensated by the interaction energy, the product of the interaction constant and the polarity density. So then, due to this condition, we can recast the Bogoliubov expression in this way, because we can eliminate delta basically. And in the very low wave vector regime, this formula is approximated by this very simple expression. So we can see here that we have a linearization of the Bogoliubov dispersion. We can see the linearization of the Bogoliubov dispersion in the low wave vector regime clearly here in this graphic. And then in this regime, so the fact that we have the linearization of the Bogoliubov dispersion is the signature that we have collective excitation in the fluid. Then for a larger wave vector, in particular when the wave vector are larger than the inverse of the Healing length, we recover a parabolic dispersion, which is the typical of single particle behavior. So then in this case, we have a normal fluid which has no collective excitation and behavior. In this region, we have a superfluid behavior. Of course, the slope here in this linear part allow us to extract this value of CS, which is the speed of sound, which is proportional to the square root of the polarity. We also have in this kind of fluid of light, we also observe the symmetric of the normal branch, the so-called ghost branch, that has negative frequencies with respect to the frequency of the energy of the polarity. Okay, so then this is a very remarkable point, because if we work with our system in this point here, we should observe a typical behavior, which is also observed in atomic Bose-Einstein condensate, that is the smoking gun of the superfluid. But then the nature, the fact that we have a driven dissipative system allow us to have also different behavior. In particular, if we increase the pump intensity and we drive the system here at this point, so far away with respect to the sonic point, we have what we observe in the parabolic, the Bogoliubov dispersion, is the fact that we have the opening of a gap. The two branches are separated in energy, and in particular, so the linear behavior is lost. So this means that now the excitation are not phonon-like, but are massive here. And so then is a specificity of the driven-dissipative system, polaritonic driven-dissipative system, which is not present, for example, in the atomic Bose-Einstein condensate. So then how it is possible to measure, this is what is predicted by the theory, so how it is possible to measure in the experiment this dispersion relation, Bogoliubov dispersion relation. So it's not an easy task, in particular in the case of resonant excitation, because the presence of the strong pump typically saturates the detection, and it is very difficult to measure the behavior of the collective excitation in the lower wave vector regime that is very close to the strong pump which generates the fluid. And indeed, these are nice experiments done in the past. They are measuring the dispersion relation, and it is indeed very difficult to have a clear evidence of the linearity or of the linearization of the Bogoliubov dispersion. In particular, this is due to the fact that it's difficult to go in the very low wave vector regime due to the fact that the detection is saturated by this. So then we have decided to try to improve this kind of measurement, developing a new technique that is called coherent probe spectroscopy that we can see here. So the idea is very simple. We have a pump, a strong pump which creates the fluid, and then we have a probe which is very weak. We can create a perturbation on the top of the fluid with our probe, and then we can scan the energy of the probe. So we fix the wave vector and we scan the energy of the probe. When the probe is in resonance with the Bogoliubov mode, it is efficiently transmitted, and then measuring the transmission peak on the reflection dip, we can reconstruct slice by slice all the Bogoliubov dispersion. The important point is that here the probe is modulated at 5 MHz, and this allows us to detect the probe via spectrum analyzer and to filter out very efficiently the pump, and then we can observe at very low wave vector. These method has a very strong, very high resolution in energy, which is fixed by the laser line, and also very high resolution in the momentum space, which is fixed by the space filtering that we are performing using the DMT. So these are the results that we have obtained. So we drive the system here at the turning point of the polarity so the stability curve, and we can see here very clearly this is direct measurement without any let's say treatment, and we can see that for low wave vector we have a linear behavior, and then we recover a parabolic one for large wave vector. So this is an interesting technique to precisely measure the Bogoliubov dispersion. I have also said that in our system we have also the negative solution, the so-called ghost branch. This is very difficult to observe in general also in the Polaritron system because it's very low. The signal is very low in the ghost branch, but we can exploit here with our pump probe spectroscopy technique. We can exploit a four-way mixing process. Indeed, when the probe is, for example, resonant with this Bogoliubov mode, generate by four-way mixing a wave vector, so a corresponding Bogoliubov mode on the ghost branch, which conserve the energy and the total momentum. So then, with this technique, we can also measure very precisely the ghost branch that you can see here. Okay, so this we have developed this technique, which is very powerful, and then we would like to use this technique in order to study a driven dissipative phase transition, and in particular show that we have a diffusive Goston mode in this system. Of course, so just to introduce the subject, so the Goston mode theorem, the Goston theorem, sorry, states that a spontaneous symmetry breaking of a continuous symmetry, spontaneous breaking, sorry, of a continuous symmetry is accompanied by the appearance of a Goston mode. The example are again the appearance of a sound mode in superfluidity U4 or in the atomic Bose-Einstein condensation is the linearization of the Bogoliubov dispersion that we have discussed before in the framework of Bose-Einstein atomic condensation, but there is also other manifestation of the appearance of Goston mode in other systems. For example, in the solid state system, we have the Magnon excitation in ferromagnets, and also the pattern formation in driven-dissipative nonlinear systems. So we are in this category, because we are studying a driven-dissipative system, which is an optical system, nonlinear. So then, in principle, we should also observe Goston mode in our system. Of course, in order to observe a spontaneous breaking of a symmetry, in this case, we would like to observe a spontaneous symmetry of a phase. We need to change the configuration, because when we pump our microcavity in a resonant with the resonant excitation configuration, we fix the phase of the Polyton fluid, and then we cannot observe a spontaneous breaking of the phase symmetry. So then we have now changed the configuration, and we use the so-called optical parametric oscillation in Polyton. So for this, we exploit the fact that the lower Polyton branch here has a specific shape, and when the system is pumped here in this specific point that in the Polyton community is called a magic angle, we can generate by four-way mixing two Polyton modes, the signal and the idler mode, conserving the phase matching conditions, so the momentum and the energy. So the Hamiltonian of the system is invariant under simultaneous and opposite phase rotation of the signal and the idler. We can see here. So then this means that the sum of the phase of the signal and the idler is fixed, but the phase difference is free. When the threshold for the parametric oscillation is crossed, so the system emits coherent beams with a well-defined phase. So this means that the phase difference has been randomly selected by the system, which undergoes a spontaneous breaking of this phase rotation symmetry. So then, crossing the threshold corresponds to the spontaneous symmetry breaking of the phase symmetry, and then we should observe the appearance of a Goston mode. This was predicted in theory by Jacopo Carusotto and Michel Bouters some years ago now in this paper, and what they predicted is in particular the observation of the Bogoliubov dispersion of this Goston mode, so the spectral signature of the Goston mode. And what the theory predicts is that the Bogoliubov dispersion of the Goston mode should exhibit an imaginary part which goes to zero for wave vector k equals 0. So this means that we should observe a very strong narrowing of the line width of the emission, because the imaginary part of the dispersion is linked to the line width of the Poynton mode. And in the real part of the Bogoliubov dispersion, also the real part of the Bogoliubov dispersion goes to 0 for k equals 0. And it exhibits the presence of a plateau for a finite range of wave vectors. So these are the two specific features of a Gaussian mode in a driven dissipative system. So the imaginary part goes to 0, so then we have a narrowing of the line, and we should observe the presence of this plateau. So the Bogoliubov dispersion in for very low wave vector is purely imaginary here. You can see here, and this means that the Gaussian mode in the case of a driven dissipative system is diffusive. So this means that the collective excitations are not propagated with a constant speed, which is the speed of sound in the fluid, but rather they diffuse and relax with the rate which depend on the wave vector. So these are the specific features that we should be able to observe. These Gaussian modes were studied in the past, which in the group of Jacqueline Bloch and Daniele Sanvito, and in particular they characterize the behavior of this Gaussian mode in Poynton in the temporal domain, observing long-lived Poynton state across the parametric threshold. Also, in the case in which the dissipation can be neglected, again, Daniele Sanvito and Dario Ballarini observed the directional Gaussian mode. So in this case, if the dissipation is negligible, then it is possible to recover a propagative Gaussian mode. But in these two works, the spectral behavior of the Gaussian mode was not addressed. And so, of course, with our technique, we are able to measure this dispersion relation of the Gaussian mode. Basically, the technique is the same. So we pump at the magic angle. We probe. So our probe is probing the signal condensate resonance, and we detect the dispersion relation, and in particular the position of the peak, the real part of the imaginary, give us the real part of the dispersion relation, and the line width of the detected peaks give us the imaginary part of the dispersion relation. These are the experimental results. So we can see that for low wave vector, in the low wave vector regime, we observe very clearly the presence of a plateau here, which is a signature of the presence of a diffusive mode. And if you observe here the line width of the peak, we can see that around k equals 0, we have a very strong narrowing of the line width, which is very, very, much more, much less than the bare Poynton line width. And for larger wave vector here, we recover a parabolic dispersion and also a line which is of the order of the bare Poynton line. So these observations are strong indication that we have indeed observed the Gaussian mode. But how we can be sure that we really observe the spontaneous symmetry breaking? So in order to demonstrate that the spontaneous symmetry breaking is really the mechanism which is at play in this experiment, we decided to do a further experiment, in particular to add a third laser beam here, injecting the third laser at the energy and the wave vector of the idler beam. So injecting with this third laser, we of course fix the phase of this idler mode, and then because the sum of the two phases is fixed, so if we fix one of the two, also the difference is fixed. So in this case, the spontaneous symmetry breaking is inhibited, so we cannot observe spontaneous symmetry breaking when we inject here the laser and we fix this phase. And so then we should observe the disappearance of the Gusto mode. And this is indeed what we observe. Here we have the line width of the Goldstone mode as a function of the tuning between the difference in energy, in frequency between the third laser and the idler frequency. We can see that when this detuning is quite high, so quite large, so the third laser does not fix the phase because it's too far from the frequency of the idler, so the injection is not effective. And then we still observe a narrow peak because the system still undergoes a spontaneous symmetry breaking. But when the tuning is near zero, we observe, so then the phase of the idler is fixed. We observe here clearly a broadening of the laser, of the line width, which is the signature that we have destroyed the Goldstone mode. So this is the smoking gun, indeed, that what we observe is really a spontaneous symmetry break. Okay, so I will go, I think that I'm running a bit late, so, but okay, I will go through the last part of the polariton, the polariton system. So, and I would like to show you that these polaritons are also very interesting platform in order to simulate different astrophysical objects, like for example, in particular to do analog physics with polarity. The idea in particular here is to try to simulate an acoustic black hole inside so using a polariton fluid. The idea, of course, is to build up laboratory experiment in which the acoustic waves behave as they were near a black hole, and then at the end could be possible to observe Hawking radiation. So how we can simulate a black hole with a polariton fluid? How we can engineer our polariton fluid in order to build up the equivalent or the analog of an horizon, for example. So this is illustrated with this cartoon. So let's consider a river here, which is going toward a waterfall. So then, of course, the velocity of the fluid, of the water of the river is increasing, not toward the waterfall. And then we can consider fish that are swimming inside the river, and the speed of fish is constant. So in this region here, on the left, of course, the speed of fish is larger than the speed of fluids. Then the fish can swim in any direction. They can go also against the fluid, okay? But the situation is different in the right region, in this region here, for example, because the fluid velocity is larger than the speed of fish. And then, of course, these fish cannot go against the flow, and they are drained toward the waterfall. So then here, where there is the crossing between the two speeds, of course, for the fish is a point of no return. No, the fish that are here cannot go in this direction. And then this is the equivalent of an horizon for the fish. Now, in the language of our fluid, okay, the water is our Polyton fluid that has a speed which is increasing, and the fish, the role of the fish is played by the collective excitation of the fluids that as I have shown you, move at the constant speed, which is the speed of sound in the fluid. Okay, so then when we have a superfluid, let's say a fluid that can be superfluid, we can define two regions, one subsonic, in which the fluid is moving at the speed which is less than the speed of sound, and a supersonic one. And at the crossing point of the two regions, we have the equivalent of an acoustic horizon. Okay, so of course the analogy is could be made in a very precise formal shape. In particular, it is possible to demonstrate that the collective excitation obey to an equation with the relativistic form of a wave equation, which is written here, the so-called Klein-Gordon equation, where eta here is the metric, which is given by this matrix, and then it is possible to demonstrate that the motion of the collective excitation in an homogeneous fluid, in which the speed is increasing, is equivalent to the motion of a scalar field on a curved space-time. What is important is that the metric of the curved space-time can be controlling two parameters of the fluid. So the speed of the fluid and the speed of sound in the fluid. And we have control on both of these parameters. Then the quantization of the acoustic field, sound inside the fluid, the quantum treatment of the sound show that the vacuum fluctuation can be scattering at the horizon, at the acoustic horizon, giving rise to the Hawking radiation that can be detected in both sides of the horizon. And what is important is to have a very sharp horizon, because this increases the strength of the expected signal. So the steepness of the horizon is given by this formula, and the interest. So what we have to do is to create a sharpest horizon in order to have the strongest signal of Hawking radiation. So how it is possible to build up an experiment? So we have done an experiment in one dimension. So the idea is to exploit here the fact that we can indeed shape the phase of the fluid, because we are in a resonant excitation. So we imprint the phase of the fluid with our laser, and then it is possible to control the speed of the fluid, which is just given by the gradient of the phase of the fluid. So we can design our phase, the phase of our fluid using a spatial light modulator, and then we can also control the profile, the velocity profile of the fluid, and we have chosen this profile here, which is a hyperbolic tangent. Okay, so then we send a laser beam with a specific phase profile. We generate a velocity profile inside our microcavity of our polariton fluid, and then at the output we can detect again the emitted beam is here, emitted field, and we can measure the density and the phase and extract so the properties of the polariton fluid inside. These are the results. So we have here the extracted speed of the fluid as a function of the position in the x direction. The fluid is flowing in this direction here. We can see that the speed of fluid is increasing in this direction here, while the speed of sound, which is proportional to the polariton density, we see here that the polariton density is nearly constant, and indeed also the polariton here, the speed of sound is nearly constant. And then we can see here at this specific precise point here, we have the crossing between the two speeds, and then at this point we have the equivalent of an acoustic horizon for the collective excitation in our fluid. We can control and change the speed of fluid at will, and then we can also control the steepness of the horizon and increase the steepness of the horizon. This means that we can control the effective space-time. So in this region here, we can see that the Mach number, so the ratio between the speed of fluid and the speed of sound, is increasing. This is a last example. We have a very strong Mach number here, equal to 4, and then this horizon here is very steep. Is the value of the steepness, and we can expect a very strong emission of Hawking radiation in this situation. Now, how it is possible to generate Hawking radiation? So we have to know now, in order to characterize the effect, we have to know the collective excitation in both the regions, in the subsonic region here and in the supersonic region here. So of course we can measure with the technique that I have explained before the dispersion radiation in the two regions, but in this case we have to pay attention, because now the fluid is not at rest, it's moving quite fast. So then we have to consider also the presence of the Doppler shift when we observe the Bogoliubov dispersion in the laboratory frame, and this modifies the Bogoliubov dispersion. These are the dispersion in the subsonic region, where the speed of fluid is quite moderate, so then they are not very strongly modified. But here, where in the supersonic region, where the Mach number is very high, we observe this strong modification of the dispersion relation. So in particular, the normal branch is pushed toward the negative frequency, and the other branch, the ghost one, is pulled toward positive frequency. So then now, if we consider a Bogoliubov mod here, this Bogoliubov mod are the group velocity given by the derivative of omega with respect to K, which is positive. So it is a perturbation which is going in this direction toward the horizon. It could be scattered by the horizon. And the theory predicts that the modes that are generated, so transmitted and reflected, in particular the Hawking radiation mode and the partner mode, are entangled. So then we should be able to measure entanglement between these two modes. In the experiment, we are indeed able to generate a situation in which we have this configuration of the dispersion relation. We can see this is in the subsonic region and this in the supersonic region for increasing Mach number. We can see here that we are indeed in a situation which is similar to the theoretical one. So now, how it is possible to generate entanglement? The idea is to start first with a simple experiment, so not to look at the spontaneous emission in which vacuum fluctuations are scattered by the horizon, because the signal is really very weak, but to observe the so-called stimulated Hawking radiation. So in this case, we can send a probe here in the subsonic region. This creates a perturbation which is propagating toward the horizon, and then it is scattered in these three modes. And the idea is to separate in the momentum space the partner and the Hawking radiation mode, optimize the detection setup in the stimulated configuration, then switch off the probe to be in the spontaneous configuration, and perform the modine detection on conjugated quadratures, and hopefully verify the entanglement. Okay, so I will conclude with this first part on polaritons. So the idea, so what I shown you is that we have developed a high resolution spectroscopy experiment in the polariton fluid, and then we have measured the dispersion relation with very high precision. We have used this technique to observe a diffused Goldstone mode in this system, and I have shown you our progress toward the observation of Hawking radiation. So I think that we can stop here for and have a break. And if you have time, I don't know if I am quite late, no? I think.
So, it is a little bit late, but don't worry about it, Alberto. I think that your lecture is very moving and very interesting because we have many questions. So we will address them first thing after the break.
Yeah.
How is the wave vector of polaritons controlled experimentally?
Okay, so yeah, this is quite simple in the experiment, because the wave vector is controlled by the angle of the excitation laser. So if I excite my microcavity exactly at the normal incidence, I generate a polariton fluid at rest with k equals 0. If I inclinate a bit my laser, so I can choose the angle which corresponds to a certain wave vector. So this is quite straightforward, simple way to control the wave vector. Yeah.
Okay, thank you. Second question. Is the photon's acquisition of an effective mass a dimensional effect? The effective one-dimensional electromagnetic field Lagrangian in a waveguide looks like that of a massive particle. About how strong should the confinement be to make such a description look valid in the microcavity case?
Very difficult question. So I think that so what we see indeed is that in the microcavity situation, but also in a simple Fabry-Perot cavity, the energy of the photon, so the resonance of the cavity, depend on the angle in which we excite the cavity, no? So then this confinement is let's say, automatically achieved in the cavity. You know, so then it's not really a difficult thing to have. So the fact that you have a cavity implies that the resonance is different with if you pump your cavity at normal incidence or with an angle, because the length of the cavity seen by the photon is not the same. And then this is automatically achieved. So this is not not to have a strong confinement, just the presence of the cavity is enough.
Okay, thank you. Next question. In your pump probe experiment, how do you distinguish between the bare LP dispersion and Bogoliubov dispersion?
Yeah.
Do they appear simultaneously in the spectra, or does the Bogoliubov branch emerge only above a certain pump threshold?
Yeah. It's true, because Bogoliubov, the Bogoliubov dispersion is due to the fact that we have collective excitation. We need a certain nonlinearity, so we need a certain interaction. So then, without pump, for example, we have just, so without pump or with very low pump, we have just the bare polariton line width. So then the normal polariton dispersion. When we increase the intensity, we have these nonlinear effects, and then we can also see the appearance of the Bogoliubov branch.
Okay, thank you. Next question. Is the destruction of the Goldstone mode reversible? Can it be restored by tuning pump conditions?
Yes, in the sense that when we change the third laser, so we destroy the Goldstone mode, injecting with the third laser and fixing the phase of the item. But if we change the frequency of the third laser, so the phase fixing is no more effective, and automatically we recover the Goldstone mode.
Okay, thank you. Next question. What are the sample considerations that we need to keep in mind while performing the black hole simulations?
What are sample considerations? So I mean, is a standard sample. What is important here is the ability to control the fluid parameter. So basically, we need to be able to control the speed of fluid and the speed of sound. But the sample per se has not to have specific characteristics. So it's a standard microcavity sample that we use also for other experiments.
Okay, thank you. Next question, slide 33. Can you provide a simple physical explanation for why the spatial derivative of phase changes the speed of sound and gives the velocity profile of the fluid in the cavity?
No, this is probably a misleading. No, the derivative of the phase changes the speed of fluid, not the speed of sound. The speed of sound is only fixed by the polariton density. Is proportional to the square root of the interaction energy, G, the interaction constant, times N, the polariton density. This is the speed of sound. So then if I have to change the speed of sound, I have to control the polariton density. So then I have to change basically the intensity of my laser. Okay, I inject more or less polariton. The phase of the fluid, and so then the derivative or the gradient of the phase of the fluid control the speed of the fluid itself, because if you think of the plane waves, you have a exponential AKR, some KX, something like this, and you take the gradient of this with respect to x, you have h bar k over m, which is just the speed. So the derivative of the phase is the speed of the fluid. So then if I am able to control the speed of the fluid, so the phase of the fluid, then I can control the speed of the fluid. And the phase of the fluid can be controlled easily because we can imprint the phase via the laser. So then we control the phase of the laser using a spatial light modulator. we inject, so we pump the cavity with this laser, and we control in this way the phase of the fluid. And then the speed.
Thank you. Next question. Do Bogoliubov type of excitations in Goldstone modes survive in laterally confined polariton systems? Do they lead to signatures also in non-resonant excitation experiments?
Okay, so the Bogoliubov type of excitation are present also in wires or pillars, so then in different confinement systems, so 0 dipolariton, 1 dipolariton. So this is okay. And I think also that, of course, they lead to signature in non-resonant excitation experiments. So it could be interesting indeed, and is one of the experiments that we would like to do indeed, to measure with the technique, the pump and probe spectroscopy, for example, the Bogoliubov dispersion of a Bose-Einstein condensate generated with non-resonant excitation. Because to the best of my knowledge, it has not been done with this technique. I mean, so in principle, we should observe something similar to what we have observed in the parametric situation, because the presence of dissipation should imply the appearance of this plateau. There are some theoretical papers that predict this kind of behavior.
Okay, thank you. And last question. So many questions for the break. Wow.
Yeah.
In atomic BCs, modulational instability comes from unstable modes in Bogoliubov spectrum.
Yeah.
Do similar instabilities occur in polariton condensate?
Okay, we can observe instabilities in polariton system, in particular when so because we are in a bistable system. So basically, if we drive our system, for example, in the vicinity of the turning point of the bistability curve, in the lower or in the upper. So here, in these 2 points, there are indeed instabilities. Modulation is sort of parametric instability in our case, that are because if you have a look at the Bogoliubov dispersion, we can see that the Bogoliubov mode have an imaginary part that start to be positive. So then there is an amplification, no? And this is generating stability. And for example, if we drive the system in the lower polariton point, so in the lower turning point, then these instability are responsible for the jump toward the upper branch. And conversely, to the jump to the lower if we drive in the upper. So then I think that are quite similar phenomena.
Okay, thank you very much. Those were all the questions in the Q&A. And yeah, the floor is yours for the second half of the lecture.
I can go for the last part. So I will try to be fast. I have 15 minutes, no? So, okay.
Well, I think like 10 past 4 is still fine.
Okay, good. Okay, so in the second part, I would like to discuss a bit a different kind of fluid of light, so the so-called paraxial fluid of light in a hot atomic vapor in our case. Okay, why it's not moving? Okay. Yes. In this case, as I already said before, pointer laser. Okay. The configuration, experimental configuration is even simpler than before because we have no cavities now. We have no cavity. We have just a nonlinear medium here, and the beam which is propagating inside. Okay. And in the case of paraxial approximation, so this means that we consider quite collimated beam, not too divergent, you know. So the propagation of this light wave in a nonlinear medium, in particular in a Kerr medium, can be described by this equation here, which is the so-called nonlinear Schrödinger equation. And we can see that we can identify really term by term this equation with the standard Gross-Pitayevsky equation: kinetic energy, external potential, and the nonlinear interaction that in this case are given by the type 3 nonlinearity of the medium and by the intensity of the light. No, there is an important difference here, because you can see here the derivative here is with respect to z and not with respect to the time. So this means that in this system in which we have this propagating geometry, the direction of propagation is equivalent to an effective interaction time. Okay? So then if I look at different planes inside the cell or inside the medium, I can follow the evolution of the system as a function of time. So also in this case, the quantum fluid are two-dimensional because they are essentially living in the transverse plane of the beam. The confinement of the photons and then the effective mass is given here by the fact that the transverse shape of the beam is Gaussian, no? Then there is a confinement. And okay, the nonlinearity give us interaction, effective interaction between photons. So then the idea is that also with this system we can have collective behavior. There are different experimental platforms in order to implement this fluid of light in propagating geometry. There is, for example, photorefractive crystals. Very nice experiments are done in the group of Mathieu Bellec and Jean-Michel Nice, or thermo-optic liquid. So in particular metal, but could be different, also different kind of liquid. Probably the first research that initiated this kind of study was Daniele Faccio, which is now in Glasgow, and also atomic vapor, which is the case that we are studying in Paris, also in the group of Robin Kaiser in Nice. They are studying this kind of nonlinear system. So we have a cell with, in particular, rubidium vapor. So we work with this rubidium T2 atomic line at 780 nanometer. And we are in a situation in which the detuning with respect to the atomic resonance is very large with respect to the Doppler broadening. So we can, in this case, neglect the fine structure of the atoms and model the rubidium atoms as a simple two-level system. The type-free nonlinearity is given roughly, so this is a sort of approximation, the two-level approximation given by this formula. Here, N is the atomic density, the number of atoms, so the atomic density in the cell. And this delta here, delta cube, is the detuning with respect to the resonance, atomic resonance. So then we can see that playing with the detuning and with the atomic density, we have two knobs to control the nonlinearities, because we can increase the atomic density, increasing the temperature of the cell, and then we can increase the nonlinearity. We can reduce the detuning and then increase the nonlinearities. Of course, we have to, so there is a trade-off to find in order to achieve high enough repulsive nonlinearities, but also low absorption, to have low absorption, because if we reduce too much the delta, we are in resonance, of course, and then the light is absorbed, and then it's not good. So then we have to stay with a certain value of the detuning and play with these two knobs in order to have the right conditions. Okay. A point that could be worth to stress is that due to the fact that we have this delta cube, changing the tuning with respect to the resonance, the positive or negative side, we can also play with the sign of the nonlinearity, and then on the interaction. So we can have repulsive or attractive interaction. In our case, we work with repulsive interaction because we want to simulate the behavior of, for example, this fluid of light. And in the case of attractive interaction, typically there are instability that are observed. Okay, so in order to have a stable system, we prefer to work in repulsive interaction. So then the question is this a superfluid? Could be a superfluid. So as before, the smoking gun is to measure the Bogoliubov dispersion, and as I have already explained, so we should be able to observe a delinearization for the low wave vector in the low wave vector region. So the small wave vector in the transverse plane, we should have a Bogoliubov dispersion which is linear in the wave vector, and the proportionality factor in the speed of sound. For large wave vector, we should recover a parabolic dispersion. In this case, the speed of sound is also proportional to the fluid density, which is, of course, in this case, proportional to the intensity of the light beam, which is sent in the nonlinear. So how to measure this Bogoliubov dispersion in this case? We have designed a specific experiment, so it's not so different with respect to the experiment that I showed before, but so there are some specificities. So the idea is we have the nonlinear medium, we have an intense, very intense pump that creates the photon fluid, no, this one, and we have a weak localized probe beam that creates a perturbation as before. So we create a perturbation on the top of the fluid, and then we look at the behavior of this perturbation, and in particular we measure. So we create the perturbation here in the input plane as z equals 0. Then the perturbation propagate along the cell in the transverse plane, and at the output we can measure the displacement of the perturbation as a function of the probe wave vector. No, we change the probe wave vector, we make the perturbation, we measure the displacement, and from this we can extract the group velocity of the perturbation and reconstruct the Bogoliubov dispersion. Indeed, what we have measured, we can see here the displacement as a function of the wave vector of the perturbation. No? And we can see that for small wave vector, basically the displacement is constant. Okay, the same displacement independently on the wave vector. This means that the speed, the group velocity of the perturbation does not depend on k, on the wave vector for small wave vector. But then, when we cross this value, we start to see that the displacement is linear in k, in the wave vector, in the state q. Okay, so then this is okay. This means that here we have a superfluid behavior, and this is we recover the standard particle light behavior. So this is the displacement. From this measurement, recalling, so remembering, recalling that the group velocity is proportional, so it's given by the derivative of omega with respect to the wave vector k on the counter plane, is very easy to reconstruct the Bogoliubov dispersion just by integration. And from the previous measurement, we can reconstruct the Bogoliubov dispersion. And of course, in the linear, when the displacement is constant, we obtain integrating a linear behavior, and then when it's linear, we obtain by integration this parabolic behavior. So we have demonstrated here that we have indeed also in this case collective behavior that is typical of a superfluid. Okay. Of course, this was done at a specific intensity, so then the value of the speed of sound is fixed. So in order to verify that the speed of sound follows the right dependence on the density, on the intensity of the light, we have to perform the experiment for different intensity and verify that is indeed a square root proportion to the square root of the. This is what we have done. We can see here the measurement, and then we can extract the N2. The N2 is the nonlinear refraction index, which is due to the presence of the chi-free nonlinearity in the medium, and the value is in a good agreement with the value measured with the independent experiment using the formation probability. So I cannot enter into the detail, but we have an excellent agreement between the two that show that this measurement is indeed coherent with what we already know in this system. Okay, now we have a superfluid, and then we can also study interesting hydrodynamics of this superfluid. There is a lot of experiment that can be done with this fluid of light in propagating geometry, study of shock waves, the study of turbulence, quantum turbulence in particular, vortex collision, mixture of fluids, quench, thermalization, formation solid, and so on. So of course, I have no time to discuss all these kind of possibilities, and I would like to show you one or two examples of what we can do. So in particular, turbulence with two counter streaming flow. So the idea is quite simple, no? Because we can generate two fluids that are counter propagating. So we send a laser beam onto an SLM, which is the phase profile is controlled in such a way that after the SLM, we generate two counter propagating beams that enter the cell here, and then they interact. Now during the propagation, they are counter propagating, then they perform a collision. And when the nonlinearity are low, in this case at the beginning at the input of the cell, of course the nonlinearity are still zero, no? We observe a normal interference between the two beams, so with the regular fringes, interference fringes. But then when we during the evolution, so we have different times here that correspond, I remember you correspond to the propagation inside the cell, because the effective time is given by this formula here, where L is the length of the cell, ZNL is an effective length given by the nonlinear interaction. So we can see that increasing the interactions, we start to see that the normal interference are the fringes are deformed, and we see the formation of solitons and vortices. These are vortices and these are solitons. So the dark spots are vortices, quantized vortices, and the stripes here, so the strings are solitons. So this system is quite interesting because it's quite easy to characterize the phase of these patterns, no? Because we can just make an interference at the output of the cell with the reference beam, and then we can get the phase. And this is not easy at all, for example, in the case of atomic BC, no? To have the phase is really difficult, if impossible. In our case, because it's an optical system, it's an optical system, it's very easy to have to do an interference and to extract the phase. And this is very important. In particular, and the full analysis of this pattern, so I have no time to explain, but is very useful to study the behavior of the so-called quantum turbulence, and in particular, it is possible, for example, to observe the inverse energy cascade in the quantum turbulence, the vortex turbulence that we have done in this paper, for example. And also this kind of system is very interesting in order to study, for example, the vortex dynamics, because in the same way that I have generated two counter-propagating beams before, I can use the spatial light modulator in order to create two vortices. No, for example, at the input of the cell, I can inject two vortices at the input of the cell with a well-controlled and fixed distance, delta R, and observe during the propagation, so then during the temporal evolution of the system in presence of interaction, how this vortex behave, no? And what is interesting is that I can also choose the sign of the vortex that I am injecting. I can inject two vortices with the same sign, so with the same vorticity. And then normally we have a repulsive interaction between them, so we can observe this pair of vortices which are co-rotating. You can see these are experiments done in atomic physics systems, and these are our data, so we can see that really very similar. We can study the dissipation of vortex energy, Brownian motion, so a lot of things. We can also do the experiment injecting opposite sign vortices, for example. And in this case, of course, we have an attractive interaction between the vortices. So then they should try to tend to merge, you know, one which the other, to collapse. And sometimes for specific conditions of the system, it is possible to observe a collapse of these two opposite sign vortices toward the so-called Jones-Roberts soliton, which is one of the only known class of solitons that are stable, dark solitons, that are stable solution of the nonlinear Schrödinger equation in 2D. Okay, so this is a really very versatile platform to study this kind of stuff, because we can control it, study in a very controlled way. So just to show you why I cannot show the, okay, let's try to, no, so I try to do this, okay. You can see my screen?
Yes, we can see
Okay,
it.
okay. Because then I can do the animation. Okay, so this is not a simulation. This is a real experiment treated in real time. So then is our experimental data. So we can see here the injection of two vortices of the same with the same sign. Okay, so we can see that they co-rotate one over the other when this is the time. So they start in a certain position and they co-rotate. And then in the case of opposite sign vortices, we can see here, they at the beginning they are separated, then they merge, they form in this point here a soliton, this so-called John Robertson soliton, and then they separate again. Okay, because because the situation, so the configuration is changed. Basically, they move toward the side of the beam, and then the interaction are less, and then they separate again. So once again, so they are separated, then they merge. Here we have the soliton, and then they finally, eventually, they separate again. So then this is an example of what we can do with this kind of fluid of light to study the interaction of these vortices in a very controlled way. Okay, so I think that I'm now at the end of my talk, and I would like, of course, to thank all my collaborators, in particular my permanent colleague, the staff. So Quentin Glorieux, which is leading the experiment on rubidium vapors, Anna Lejanic, which is also permanent researcher in our group, and she's studying more nanophotonics experiment that I didn't present here. For the polariton experiments, in particular for the measurement of Bogoliubov dispersion and the Goldstone mode, I would like to thank Ferdinand Claude, which is not on this picture because it was already in postdoc, but he was a real fantastic student. And for the black hole experiment, we have Kevin Falk, Kilian Guerrero, and Maxime Jacquet that are doing a great job on this part. So then here we have the rubidium vapor team, Clara. We have Alix, Miran, which is playing with these vortices, collision between vortices and so on. And then I would like also to thank all my collaborators around the world. So thank you very much for your attention. Thank you. Thank you so much.
Thank you very much, Alberto. We have just one question, so probably you have satisfied all of the questions after the break. So let's start with the question. Could you please repeat how do you slice the images in RB vapor cell in order to study time-space dependence? You change the focus of the objective or you insert a screen inside?
No, okay. This indeed is a good question because so it's a nonlinear medium, no? So then indeed you cannot image inside because when you use optics, so what is well defined is linear transformation, no, in imaging plane and so on. So because there is a nonlinear medium, we cannot image inside. So what we do is we measure always at the output of the cell, but we rescale the time, changing the nonlinear interaction. So basically, changing the density of the polariton fluid, or the rubidium fluid, of the fluid of light, we can change the effective length, propagation length of the beam. So basically, the cell is always the same length, L, but the effective time is given by L divided by, I think that I have the formula somewhere. Sorry, so is number where is so is L divided by Z and L, which is the effective nonlinear length, which depend on the intensity. If you increase the intensity, you decrease the characteristic interaction length, and then you increase the effective time. But then the image is done always at the output.
Okay, thank you very much. I don't see any other questions. So
Okay.
thank you. Oh, okay, sorry. We have one more question. One last question, and then we wrap it up. Given the coherent vortex dynamics you are showing, have you considered if your system could support persistent current states, say in ring geometry?
It could be possible, yeah. So indeed, there is a lot of possibility. We are just trying to study in a systematic way for the moment the interaction between vortices. But yeah, we can also do, of course, create a ring excitation and try to see if we can study this persistent current in this. Yeah. For the moment, we didn't do, but it's a possibility. Yeah.